This is a pretty example where we have two charges and we want to find a place where we could put a third charge where it wouldn't have any force. So we have charge Q1, that's plus Q, that's placed at the origin. And we have charge Q2, that's equal to negative 2 times Q. So it's twice as big as Q1 and oppositely charged. And that's placed at x equals 5 millimeters. Where could we put our charge Q3 so the net electric force on Q3 is equal to 0? So the net electric force on Q3 is going to be the force due to charge 1 and the force due to charge 2 added up. There are going to be two forces on charge Q3. If we want the net force to be 0, it means those two forces, due to charge 1 and due to charge 2, they're going to have to cancel. They're going to have to be equal and opposite. So I think that might be a note worth making. So F by 1 on 3 and F by 2 on 3 must cancel, so they're going to have to be equal and opposite. So we have to find the spot where those two forces are going to be equal and opposite. We kind of have three general areas to look at. We could be left of Q1, between Q1 and Q2, or right of Q2. Let's look at the three general areas, narrow it down to one area, and then find the specific position. Let's start with between Q1 and Q2. So what would happen if we put our charge Q3 in the middle there? So let's say that I put my charge Q3 right here. We might notice here that we don't know if Q3 is positive or negative. I'm just going to call it positive for right now, and hopefully we can sort out the idea of does that even matter later on. Well, if we put Q3 right here, we have Q3 and Q1, both positives. Q3 will be repelled by Q1, so the force on it is going to be to the right. It's repelled, it's pushed away. So there's F13. What about the force between 2 and 3? Well, those are oppositely charged, so 3 is going to be attracted to 2. The force is going to be to the right. 2, 3. So now somewhere between the charges, the forces could have equal magnitude, but they'll always have the same direction. They can never be opposite, so they can't cancel. So not opposite. Can't cancel. So this spot is not our choice. Okay, how about to the right of charge Q2? Let's put a force out there and see what happens over there. So let's put our Q3 right here. So here we have Q3. Oh, I better label that. Q3. Q3 and Q1, let's think about those forces now. Q1 is positive, Q3 is positive. Q3 will be repelled by Q1. It's going to be pushed to the right because of Q1. Now let's think about the magnitude of that force. Q1 is small charge, and we're very far away from it. It's going to make a small force. So the force by 1 on 3 is a small force. Between Q2 and Q3, they're oppositely charged, so it's going to be an attractive force. Q3 will be pulled to the left because of Q2, but Q2 is a big charge, and we're very close to it. We're going to have a big leftward force here. So let's draw that guy, F23. So here, they are opposite, but they're not equal, and they can't be equal. So there's no place where those could have equal magnitude. Okay, and that's because F13 is always smaller than F23 because we're close to a big charge and we're far away from a small charge. So can't cancel. That gives us one last place to look at, and that's to the left of Q1. So if we put our Q3 out here, we're repelled by Q1, that's a force to the left. Now we're kind of close to a small charge, that gives us a medium force. And Q3 and Q2 are opposite, it's going to be attractive. Here we're far away from a big charge. Again, we're getting kind of a medium force. Okay, here's where we can have the two forces equal and opposite. So to the left of Q1 is our winner. This is the place. So it must be left of Q1. All right, let's see how we're going to figure out exactly how far left. Well, we know that the net force is equal to 0. So F12 plus sorry, I got my, yeah, that's right, F13, sorry, I knew I made a goof there, plus F23 have to be equal to 0, which tells me that the magnitude of F13 is equal to the magnitude of F23. Okay, I already know they're opposite because they're opposite directions when I'm left of Q1. So the last part I'm trying to fill is making the magnitudes equal. So my next step, I'm going to fill in Coulomb's law and I'm going to solve for my distance. Let's now fill in Coulomb's law to find the magnitude of the electric forces and solve for the distance. So the magnitude of 1,3 equals the magnitude of 2,3. Magnitude of the electric force between 1 and 3 is K times the magnitude of Q1 times the magnitude of Q3 divided by the distance between 1 and 3 squared equals K times the magnitude of Q2 times the magnitude of Q3 divided by the distance between 2 and 3 squared. Okay, there's some stuff to unpack in this equation. Let's go through it one by one. First, we could divide both sides through by K and we see that they cancel. Second, we could divide both sides by the magnitude of Q3 and they cancel. Okay, that's a pretty interesting note. The charge Q3 cancels. That means the position where we could get a net force of 0 doesn't depend on the charge itself. So we could have picked a negative charge or a positive charge, that didn't matter. And it didn't matter what size of a charge we picked. This is kind of a hint that something is coming related to this topic. Okay, last little thing we'll talk about is R13 and R23. Let's get those distances on the diagram and see how they're related. So Q1 was our plus charge, that's Q1. So R13 is from here to here. Charge 2 was our green charge, Q2. So R12 is from here to here. Let's see if they're related at all. Oops, sorry, that should be R23, not R12. So many subscripts, sometimes it's easy to make a goof. 2, 3. So are they related at all? Well, the distance between Q1 and Q3 is 5 millimeters. So if we look at our setup here, what we can see is that R13 plus 5 millimeters equals R23. So then that would tell us what we can fill in for R23. So we can put this expression in right here in this equation. Then we'll be able to solve for R13. So our answer will be the distance where we get the 0 force on charge 3 relative to Q1, which was at the origin. So that was our x equals 0. Okay, let's get started on that step. So I've got the magnitude of Q1. So that's positive plus Q. So Q divided by R13 squared equals the magnitude of charge 2. It's a negative charge. When we do the magnitude, we drop the negative, equals 2Q. So 2Q divided by R23 squared, which is R13 plus 5 millimeters squared. If you wish, you could put your 5 millimeters in meters. I'm going to leave it as millimeters. All right, now I've got a Q on top and bottom of both sides, so they cancel. Last, let's look at how we're going to solve this. If you wish, you could cross multiply and solve a quadratic. I'm not a big fan of solving the quadratic, so I'm going to take the square root of the top and bottom of both sides. So square root of 1 is 1, square root of R13 squared is R13, square root of 2 is root 2, square root of R13 plus 5 squared is R13 plus 5. Okay, we'll go on to the next slide and then we'll solve this equation. Next step in solving this problem is to cross multiply, so R13 plus 5 millimeters equals root 2 times R13. So root 2 minus 1 times R13 equals 5 millimeters. So R13 equals 5 millimeters divided by root 2 minus 1 gives us an answer of 12.1 millimeters. Okay, let's take stock of our answer. And our answer tells us that any charge placed at 12.1 millimeters left of Q1, or x equals minus 12.1 millimeters, that charge will experience zero net force. So if we could gently lay a charge right there, it would be at equilibrium and it wouldn't move. Let's do an example now where we take full advantage of the symmetry to get our answer. We've got 4 1 microcoulomb charges, so I'm going to say little q is 1 times 10 to the minus 6 coulombs. My top left charge I'll call Q1, that's plus Q. Top right is Q2 equals plus Q. Bottom left is Q3, that equals minus Q. And bottom right is Q4 equals minus Q. They're arranged on a square of side length 1 centimeter. I'm going to represent that by a D. And I pop an electron, that's a little negative charge in the center of the square. I want to find the net force on it. The first step in the process is to draw the free body diagram. So my little electron will be attracted to charge Q1 because negative and positives attract. There's my force on the electron due to charge 1. It will be attracted to charge 2. There's my attractive force on the electron due to charge 2. It will be repelled by charge Q3. There's F3. And it will be repelled by charge 4. There's F4. Those forces are all along the diagonal of a square, so the angles have to be 45 degrees. We'll need that when we find our components. Okay, next step in our process is to find the magnitudes of the forces. The magnitude of the force on the electron due to charge 1 is K times Q1 times the Q of the electron divided by R squared. Okay, Q of the electron is minus E, minus 1.60 times 10 to the minus 19 coulombs. R is the distance between charge 1 and the electron. That's a half the diagonal of the square. So R is the hypotenuse of a right angle triangle where the legs are D over 2 and D over 2. So we can calculate our R. It's the square root of D over 2 squared plus D over 2 squared, which is root 2 over 2D. Okay, let's put our things in our equation now. Oh, we might want to pop in that K is 8.99 times 10 to the 9 newtons meters squared over coulombs squared. So we've got K times 1 times 10 to the minus 6 coulombs times 1.6 times 10 to the minus 19 coulombs. Notice I'm putting in the magnitudes of the charges divided by R squared, so root 2 over 2 times D squared. Put all that through your calculator and you should get 2.88 times 10 to the minus 11 newtons. Okay, what's interesting here? Q1, 2, 3, and 4, they all have the same magnitude of charge. They're all equidistant from that electron. So by the symmetry, all of those forces have the same magnitude. Okay, so that's the magnitude of the forces done. Next, we'll need to find the components. So my components of F1, so F1 is up and to the left, F1x is left, F1y is up, taking positive x to the right and positive y up. So F1x is equal to minus F1 cosine 45. Do that in the calculator. Well, we don't really need to do fx in the calculator, but we can if we want to. Yeah, I think maybe I won't. And f1y equals plus f times sine 45 degrees. Okay, let's get the rest of our components. So f2x points to the right, it's positive. It has a magnitude of f2 times cos 45. The y component of f2 is positive because it points up. For f3, the y component is positive because it points right. Oh, sorry, I mixed that up. For f3, the x component is positive because it points right. The y component is positive because it points up. And for f4, the x component is negative because it points left. And the y component is positive because it points up. Okay, step 1 was the free body diagram. Step 2 was the magnitude. Step 3 was the components. Step 4 is to do our vector addition. I'm going to do that on the next slide. So let's move on to the next slide. So our net force in the x direction, sum Fx, equals plus F cos 45, minus F cos 45, plus F cos 45, plus F cos 45, minus F cos 45, equals 0. So the x components of all those forces sums to be 0. What about the y components? Sum Fy is plus F sine 45, plus F sine 45, plus F sine 45, plus F sine 45. We've got 4 of those guys that are the same. So 4 times F1, remember F1, 2, 3, and 4 are all the same, times sine 45 degrees. Pop that through the calculator, remembering that F1 was 2.88 times 10 to the minus 11 newtons. And we get 8.14 times 10 to the minus 11 newtons. So the x component is 0 and the y component is 8.14 times 10 to the minus 11. We write our answer as a vector to finish up, and we get F equals 8.14 times 10 to the minus 11 newtons up or in the j direction. As a homework problem, use F equals ma to find the initial acceleration of the problem, and then repeat the problem if we had a proton there instead of an electron.